Our final lesson in Chapter 7 is Lesson 7.6, Solving Exponential and Logarithmic Equations. We'll first start by solving exponential equations. We want to isolate our base, and remember the base is whatever part has the exponent. Sometimes we may need to move things over by adding, subtracting, multiplying, or dividing. Then what we're going to do is take our exponential equation and convert it to logarithmic form by looping. Once we have it in logarithmic form, we're going to solve by applying the change of base rule. You're going to want to make sure you have your calculator with you today. So grab that and let's solve the problems down below. We're asked to solve each equation, and for this section we're going to round to the nearest hundredth when appropriate, and that's 2 places past the decimal. Question 1, 4 to the x power is equal to 11. Well, that's not on our power chart because 4 to an integer exponent doesn't get us 11. We'll use the converting to logarithmic form rule to help us here. Now 4 is our base, and notice it's isolated on that left-hand side, 4 to the x power. Step 2, if we convert it to logarithmic, remember when we do this, we just use log, keep our base, that little sub 4, and then we loop. What are we taking the logarithm of? 11. What do we want it to equal? Well, that's our exponent x. Notice in this form, our variable is already isolated, but we need to round to the nearest hundredth. So to do that, we're going to apply the change of base rule. Now remember, you could use log or ln, and they both would give you the same result. The change of base rule is just going to convert us to base 10 by typing in log of 11 divided by log 4. Remember, whatever the base is, oh, I almost made it tiny. We don't want to do that. Whatever the base is, make sure you put that logarithm in the denominator. All right, type that in, would you please? Log 11 divided by log 4, and then press enter. You should get x equals approximately 1.73 for our value of x. And you could check that. If you checked it by plugging in 4 to the 1.73 power, you get approximately 11. So remember, the logarithmic function is just the inverse of that exponential statement. All right, let's try question 2 on the right. In this example, we have 6 to the 2x power plus 7 equals 19. Recognizing that our base has the exponent, and that's the base of 6. First, I'm going to move the 7 over by subtracting. We get 6 to the 2x power equals 12. Now convert to logarithmic by looping. We'll do log, base 6, and then we're going to loop it of 12 equals our exponent of 2x. Okay, so now convert the left-hand side using your change of base rule. I'm just going to kind of move this over here to the side because I tend to write too big and I'm going to run out of space. If we convert this to the change of base rule, log 12 divided by log 6 equals 2x. I'm going to do something a little bit unconventional here, and I'm going to actually divide by 2 at this point to get x by itself. As we type this into our calculators, what we have to recognize is once you put log on your calculator, it'll give you that left parenthesis. What we have to be careful of is making sure that we put that right parenthesis in before we divide by log 6. And again, make sure that if it defaults a parenthesis on one side, you close it on the other side. Please type in log 12 divided by log 6 divided by 2, and let's see what you get. We should get approximately 0.69. All right, try question 3. 5 to the x equals negative 25. Notice our base is isolated, so we can go right to step 2, convert to logarithmic. If we type in log base 5, we want to take it of negative 25. And then our answer will equal x. Now, applying the change of base rule here, we'll have log of negative 25 divided by log 5. That gets x by itself, but watch what happens when you plug that in. You should get domain error or no solution. Remember, we can't take a logarithm of a negative number. So even if you notice that right at the beginning, 5 to the x, we can't raise 5 to an exponent and get a negative answer. So this is automatically no solution. Now in example 4, we're still doing solving the equation, and we're still going to loop to logarithmic, but now notice our base is e. Instead of using our log prefix, we're going to use the ln prefix for natural logarithm. We have 1/3 e to the x equals 2. We have to be careful here because our base is that e to the x. We need to get the 1/3 to the other side, so I'm just going to multiply both sides by 3. And that'll cancel out with the 1/3 and giving us e to the x. On the right-hand side, 3 times 2 is 6. E to the x is isolated, so in step 2, as we convert to logarithmic form by looping, remember base e means we're going to actually use ln, like I said, instead of log. So when we type ln, remember we don't write our base of e because we already know it defaults to e. So right away I'm just going to loop. We're going to take the ln of 6. And what will that equal? Well, that'll equal x. So this is going to be one of the very rare scenarios that we don't have to type that base in. On your calculator, find ln, press 6, and enter. And we should get our x value to be approximately 1.79. And those are our values rounded to the nearest hundredth. Notice each time we got x by itself first before we typed it in. And the purpose for that, everybody, was to make sure that we only rounded one time, and that was at our final answer. Now that we've worked with a few exponential equations, what happens when we start with a logarithmic equation? Now remember, a logarithmic equation is going to be any equation with log or ln. The first thing you want to do is very similar to what we did up above. You want to isolate the term you're trying to solve for. In this case, it's going to be a logarithmic term. Now remember, what we have to be careful with here is you have to take the logarithm of something. So it's not just log or ln, it's log of x or ln of x plus 4. So a term has to have log or ln and then your base and then of something. That would be the entire term, not just the prefix log or ln. From there, step 2, we're going to convert it to the other form. So we'll convert back to exponential by looping. From here, we'll have to either use our power chart or guess and check to determine what value makes our variable a true statement. Once we solve, we're going to test for extraneous solutions. And what we're looking for with that is when we plug our value back in for x, is we can't have either log or ln of a negative number. That kind of value would make, or that kind of equation would make our x value extraneous. All right, let's try a couple here at the bottom and see how it goes. We're asked to solve each equation. And again, like we did up above, we'll round our answers to the nearest hundredth when appropriate. Now this first example is fairly unique, so let's zoom in and see what we're working with. We have log base 5 of 5x plus 9 is equal to log base 5 of 6x. Now this kind of equation, when you have a logarithm with the same base on each side, was very similar to solving our exponential equations back in 7-4 when we tried to get our bases to be the same, and we used our power chart to help us. In this situation, if you have a logarithm on each side of the equation, whatever we're taking the logarithm of has to be equal to each other as well. So in this scenario and the scenario alone, we can actually eliminate the log terms and just solve 5x plus 9 equals 6x. Now from here, this is just algebra. Move 5x to the other side, and we get x equals 9. Pretty simple. Now to test it, to plug it back in and check, what we're looking for is a number when we plug it back in and we get a negative value. So if we type in log, or plug in log base 5 of 5 times 9 plus 9, well 5 times 9 is 45. 45 plus 9 is 54. So far, so good. log base 5 of 54. On the right-hand side, if we have log base 5 of 6 times 9, we also get log base 5 of 54. That means our check is valid and x equals 9 is the correct solution to this logarithmic equation. Let's try example 6 on the right. Log base 4 of x equals negative 1. So at first it might look like this isn't possible because we have a negative in our equation. But remember, a logarithm can equal a negative value. We just can't have x be negative on the left-hand side with the log. So from here, log base 4 of x is our logarithmic term. So step 1, that's where we want to get to. Step 2, we're going to convert it back to exponential. Our base is 4, so when we convert it back to exponential, we get rid of that log term. We have to raise it to the negative 1 exponent, and that's going to get us to equal x. Now, 4 to the negative 1, we know our negative exponent properties. That's just going to make it 1 over 4 to the positive 1, which is just 1/4. And that's solving. Really, we got x by itself that quickly. Now to check it, remember we have to plug it back in the beginning. Log base 4 of 1/4, does that equal negative 1? Well, yeah, because 4 to the negative 1 equals 1/4. Notice it's positive, so we can plug that in, that's valid. When we loop it, we get a correct exponential statement. So far we're 2 for 2. Question 7, 4 times the natural log of negative x plus 3 is equal to 21. What value of x will make this true? Well, we want to first isolate our logarithmic term, so we have to be careful here. The ln negative x, that is our logarithmic term. We need to get rid of the 4 and get rid of the 3. Now the order we do that is important. Get rid of anything that's added or subtracted first, and then we'll get rid of anything that's being multiplied or divided. That still gives us 4 ln negative x on the left, and on the right we get 18. Now divide both sides by 4, so this isn't so bad. And just like that, our logarithmic term ln negative x is isolated. On the right, 18/4 is the same as 9/2. From here, recognizing that converting to exponential, ln is always base e. So if we start with base e, that gets rid of the logarithmic kind of prefix. We'll raise it to the exponent of 9/2. But notice, everybody, it equals negative x. And again, we want to just make sure that we get x totally by itself. That way we're only rounding one time when we plug things into our calculator. To get x by itself here, I'm just going to divide by negative 1. Cancels out. So you're going to want to type in e to the 9/2 power divided by negative 1. Take a moment to try to do that, plug it in, and then when you're ready, press play. You should get approximately negative 90.02. And if we plug that back in for x, that's going to make x positive on the top. So just a really quick check. If we plug in 4 times ln, remember x was already negative in the direction or in the original equation. So if we type in negative 90 or substitute in negative 90 in its place, the two negatives are going to cancel out. Plus 3 equals 21. We get a positive on the inside, so our check is valid. Example 8. Log base 2 of x plus log base 2 of x minus 2 is equal to 3. Now, unlike question 5 up above, where we had a logarithm on each side and we just canceled them out, we actually can't do that here. The two logarithms are on the same side and there's a constant on the right. So that means we can't just kind of solve the x and the x minus 2. But what we can do is condense the left-hand side using our properties of logarithms. So I'm just going to write condense underneath here. And we condense addition by multiplying the two logarithmic terms. Condensing means you're going to just break this down into one logarithmic statement, but we're going to have to do x times x minus 2 and set that equal to 3. Now notice, instead of having two logarithms, now we only have one. And we have everything isolated on that left-hand side. So there's nothing else being added or subtracted to that logarithmic term. Step 2 then, we're going to take our base of 2, and that allows us to cross off our logarithm. We're going to loop it to the third power, and then set it equal to the product of x times x minus 2. On the left-hand side, 2 to the third power, we can evaluate that. 2 times 2 times 2 is 8. Here's where it's going to be very interesting. If we have x times x minus 2, and we multiply them together, all of a sudden this becomes, oh yeah, quadratic. Anytime we have a quadratic in part of our process, we have to set everything equal to 0 and factor. So we did this last chapter, we did this in chapter 5, we even had this in chapter 4. It's not going away. What this means we have to do now is move the 8 to the other side so that we have our quadratic equation equal to 0. Hopefully, this is factorable. If it isn't factorable, we have to do quadratic formula. And there might be instances where that happens, you guys. So be ready. All right, let's see what happens. We have negative 8. I know that 1 times 8 and 2 times 4 are my choices. Is there a way to multiply with one of them being negative to get negative 8, but when we add them, we get negative 2? I think we can make this work. Positive 2 and negative 4. So if we do x plus 2 and x minus 4, that means we can get a value for x of negative 2 as an option. And then for the other one, if we add 4, x equals positive 4 is our other option. So we know we're going to have to check both of these. Hopefully they'll both work, but if not, one of them could be extraneous. So let's check negative 2 first. And already watch what happens. If we plug in log base 2, but we substitute in negative 2, right away that's not possible. Even if we plug it in for the other one, notice we'll have negative 2 minus 2, and that would be log base 2 of negative 4. We can't take the logarithm of a negative number. So because that's not possible, x equals negative 2 is extraneous. It solved our quadratic, but when we plug it back in, it doesn't solve our equation. Hopefully 4 works, so let's double check that one. If we plug in 4, we have log base 2 of 4, so far so good, plus log base 2 of 4 minus 2, and that would be a positive value as well. So notice we're good here, we're good here. 4 is a valid solution for x. Now that we've had some practice solving both exponential and logarithmic, let's take a look at some application. Question 9. Biologists have found that an alligator's length L in inches and weight W in pounds are related by the function L equals 27.1 ln W minus 32.8. I know, that all just sounds so random. It says estimate the weight of an alligator that's 10 feet long. All right, what do we know? We have two variables that we're looking at in this equation. We've got L, which is the alligator's length, and W, which is the alligator's weight. We have a formula to use, so we don't have to make anything up. That's best case scenario. I'm going to start by just rewriting that formula. The length of the alligator is equal to 27.1 times ln W, which is the weight of the alligator, minus 32.8. It says estimate the weight of the alligator that's 10 feet long. So notice 10 feet long, that is the length. But here's where it gets a little bit tricky. Up in the word problem, it said that the length was measured in inches. And if we know that the alligator is 10 feet long and there are 12 inches in every foot, we're actually going to plug in L equals 120. And we're plugging it in on the left-hand side. What? All right, so that's what we got to do. That's the length of the alligator. 120 equals. Everything else on the right is going to stay as is. 27.1 times ln W minus 32.8. From here, this is just a logarithmic equation like the problems we just did. If we want to isolate our logarithmic term, we have to get ln W by itself. What I'm going to ask you to do first is move that 32.8 over by adding. 120 plus 32.8 is 152.8. Equals 27.1 ln W. Oops, 1, there we go. Now to get ln W by itself, we have to divide by 27.1. I'm going to go out on a limb here and say that 27.1 doesn't go into 152.8 evenly, so I'm going to leave it as that fraction. It's kind of messy, I know. Okay, so I'm just going to move over here and say that 152.8 over 27.1. Whoops, put the decimal in the wrong spot. We'll fix that. There we go. Equals ln W. That's all step 1, everybody. We've isolated our logarithmic term. Step 2, let's convert it to exponential by looping. We know that our base has to be e because that's the inverse of ln. What are we raising e to the power of? That crazy fraction. So try your best to write this as small as you can. 152.8 over 27.1. That's pretty good. And then what will it equal? Oh, yeah, the weight of the alligator. It makes a lot of sense. All right, try to type that in. E to the 152.8 divided by 27.1 power. We should get the weight of the alligator to be approximately 281.01, and the label for the alligator's weight was in pounds. So there's an application problem with logarithms. And that's where we'll end our video lesson for today. We'll finish the rest of these application questions tomorrow in class.